Have you ever wondered how a computer understands not just the individual words you type, but the actual grammar and structure of your sentence? It is one thing to know what dog and bites and man mean, but how does the computer know who is doing what to whom? Word embeddings, in their most basic form, do not inherently representing word order syntax. Instead, they primarily capture semantic relationships between words based on their co-occurrence patterns. However, advanced embedding techniques, especially those from modern natural language processing models like transformers, cleverly incorporate or learn word order information to truly grasp sentence structure. The fundamental why behind this lies in the evolution of embedding models. Earlier static embeddings, such as word-to-vec or glove, assigned a single vector to each word regardless of its context. These vectors were excellent at capturing semantic similarities, for instance recognizing that king is to man as queen is to woman. However, they could not differentiate the meaning of dog bites man from man bites dog because the vectors for dog, bites, and man would remain as the same, failing to capture the crucial syntactic roles determined by their positions. This limitation meant these models struggled with understanding the actual structure of a sentence. Modern contextual embeddings, notably those generated by transformer models like BERT or GPT, overcome this challenge by processing words dynamically within their sentence context. Instead of a fixed vector for each word, these models produce an embedding that is unique to the word's specific usage in that particular sentence. This is achieved through mechanisms like self-attention and, critically, positional encodings. Positional encodings are special numerical signals added to the input embeddings that explicitly tell the model the absolute or relative position of each word in the sequence. This combination allows the model's internal layers to learn how words relate to each other based on both their meaning and their position, effectively understanding syntax. The ingenious part of this process is how transformer architectures, with their self-attention mechanisms, can weigh the importance of different words in a sentence when computing a word's representation. For example, when processing the word bites in dog bites man, the model can attend more strongly to dog as the subject and man as the object, because positional encodings have already informed it about their relative locations. This allows for the implicit learning of subject-verb-object relationships and other complex grammatical structures, far beyond what static embeddings could achieve. The sinusoidal functions often used for positional encodings also provide a clever way to scale to sentences of varying lengths without needing new parameters. Ultimately, the evolution of word embeddings from static representations to dynamic, context-aware vectors augmented by positional encodings has revolutionized how machines understand language. This sophisticated approach enables natural language processing systems to move beyond mere word meaning to comprehend the intricate grammatical relationships and structures that govern human communication. By understanding how words interact based on their order, these advanced models can accurately interpret complex sentences, translate languages with greater fidelity, and answer questions with a deeper grasp of linguistic nuance.